Welcome to class number 12. We're going to be covering non-uniform distribution of mass, some transient processes, or at least an introduction to them, and we're going to do some additional examples. So let's begin. All right, I think I'm going to switch over to the document camera. Just want to try to fix some of the things that I put up onto this. I copied these images, and I don't think from what we've written right here it quite makes sense for what was actually being trying to discuss. Right. So we're starting with a particular scenario. Let's say this is a what if. If we had like a mass of A and mass of B in two containers, and they were attached, but had a valve shut off between the two, and then you were to open the valve, and then you'd get an equilibrium between them. How would they mix? So the first thing what you would want to do is apply the conservation of mass to the system. So the mass before mass 1 is going to equal the mass after, right there. So that's the conservation of mass idea being applied to this. And then you could sub-separate mass 1 into mass 1A and mass 1B, right? So that's A and that's B. Flip back and forth. All right. Something that I want to bring to your attention also, just a nomenclature. We often will call this conservation of mass idea, or the equation for it, the continuity equation. Continuity equation. That's a big time equation. A big time name equation, so it's an important one right there. All right, so, and we'll find for many treatments that we will do for problems, we'll use the conservation of mass and the conservation of energy, or just energy equation if we want to go here. I didn't write the in-between equation for this, and maybe we would say that we liked early on, we used this form of it where we went delta E was equal to, and then we started writing things out, but we can leave off the kinetic energy and potential energy, and maybe just think of it as the internal energies for a particular mass, because this is still a particular mass, even though we've separated into two parts and they're about to get joined together. And they're going to be Q1 to 2, and then work 1 to 10. Right there. So we're still applying these. They are indicating right here lowercase e, which could be either U or H, right, to indicate. And that's on a per mass basis, and they're multiplying it by mass. And that way we're able to separate a particular set of energies in here by doing it on a per mass basis and then multiplying it by the mass. And then what they've done is they've go ahead and notice that we're going to have, inevitably, we're going to have mass 2 here, so we could divide all the way through everything by mass of 2. And in our particular situation, we'll say, well, let's go ahead, and I won't do it all the way around, but we could insulate this. That's what I'm drawing out here, your insulation around there. So no heat can get out of this. And although the systems will intermingle and change, there's no external work possible because these are going to be rigid bodies, right? So we have that work is 0 because the volume is going to be constant, and we have there's no going to be heat transfer to the outside. So this is what we often call, by the way, this is called adiabatic, right? So that's a good, also another good term to keep in your lunch pal. I don't know why I just said that. It seemed kind of weird. All right. So anyway, from this, we could just separate. Well, we could find what the end result internal energy of the system, and that's going to be of both of these after they've come to equilibrium and are steady, can be found by this mass fraction right here of them. And then also when we're done, another thing to keep in mind, we can find what the specific volume will be. So in doing so, we could actually probably figure out with these two pieces of information right here, we could actually get, for most substances, we could get what the rest of the information is with the pressure and the temperature. And then later we could find what the entropy is going to be, and then also the enthalpy, right? So this is the idea, is we can use these two equations in this way. But there's a bunch of other scenarios that we're going to come up with. So this is just one of many that we can that we might want to use and reason our way out. But it's very representative of the kinds of problems that we do in thermodynamics, where we say, we give you a scenario, and then you need to think through how to get to the desired result. Many times, the conservation of mass and the conservation of energy are the main things to go to. So, do I want to do the example? I'm making a second video. I'm going to make a second video.